Okay, let us see how we handle this example. Now here we are going to use the differential method when we are getting time of the closest distance. So particle A initially at the origin means the position vector of it before time elapses, or at t equaling to 0, before any time elapses, is this at the origin. Moving with the velocity of negative 1, 2. So negative 1, that's the velocity of A. This is the ij notation, but you can write it as a foreign vector. And particle B initially at a point negative j plus 3, negative I plus 3j, this is it, moves at 2I plus 2j meters per second, as it's there. Find part A, displacement of A relative to B at any time. So there are many methods you can use, but I think you can take this. If you want A relative to B displacement at any time, to say it's R of A initially minus R displacement of B initially, then plus the velocity of A relative to B, then times T. So that's the easiest way. This is the same as VA minus VB. So you first get this, then you substitute there. So our A, velocity of A relative to B, is going to be velocity of A, and that's velocity of B, which will be, now our velocity of A is negative 1, 2, then the velocity of B, which is 2. And from there, you can see that 9A TB is going to be negative 0 meters per second. After that, I can come and get now my part A, which is A relative to B. At any time, say the first A, its initial position, then minus the position of B initially, then plus A relative to B into T. Then this one, it means that this is the initial position. Here we are multiplying, so this one we are multiplying this and this. So don't be confused. So this one is going to be now, position initially, this is 0, minus of B initially, negative 1, 3, then plus negative 3, 0, then times T. And this is it's going to be, this is going to be 1, then this minus, this is going to be negative 3, then plus, it's going to give us negative 3t plus 0, which we can every simplify to A R of B at any time t as, and give it as 1. It's going to be 1 minus 3t, then this is will be negative 3 with ease. Okay, so then part B, the time of the closest. So this is hour, then we give it in meters. Okay, now this is part A, then they want us time when they are closest to each other. So the idea I'm going to use, of course, I told you, you can use the vector approach here of getting this, then dot this, it will be 0. Now we have seen how to use that. Now let me use that differential method. So there, our distance is going to be, we say to get time, we get the derivative of this, then square it. So our d dt of modulus of r, A relative to b at any time t is squared. So we need this one now and get its derivative. So modulus of this squared. So modulus of A, R and B at any time t squared is going to be, you see we are going to square this, 1 minus 3 t squared, then plus negative 3t squared. Okay, and this will give us 1 minus 3t squared, then plus 9. We can easily differentiate this. Okay, so now our d dt or modulus of a. This is square, that's why I don't have a square root here, because we are squaring it. This will be now d dt of, you can, if you want, you can expand this, or you can differentiate it at once. 1 minus 3t, the whole squared, plus 9. When you differentiate that, we shall get, when you differentiate this, we get 2 into 1 minus 3. Then power 1, then plus 0. Sorry, don't always forget to differentiate the brackets, because there we are using the idea of our rule. So there, after we lower the power, we reduce the power by 1, and after we differentiate the bracket, when we differentiate this, we get 0. When we differentiate this, you get negative 3. Then plus, when we differentiate this, we get 0. So the whole of that should be equaling to 0 to get our the shortest distance at the minimum. The derivative of this square should be equaling to 0. Like we know in differentiation, when you want to get the minimum time required for you, you differentiate this and then you equate to 0. So the whole of this is equaling to 0. So meaning we have this one, we shall be adding negative 6 into now 1 minus 3t equaling to 0. And that's going to give us negative 6 plus 18 t equaling to 0. And from there you can say our t is going to be a third. That is the time of the closest. This is then our part C. We come and we get the distance. Shortest distance. Our shortest distance, or is our shortest distance is going to be modulus of A R, then when we put in our third. Okay, so now our D, first of all, we come and we put our third into this. So our A into a third is going to be now 1 minus 3 into a third, then negative 3, which will give us, this is going to be 1, 0, then negative 3. So now our D will be the modulus of, at this time, which will be the square root of 0 squared plus negative 3 squared. So here is that our D is going to be 3 meters. So that's the distance of the closest approach. Oh, always don't forget when we get the modulus of this squared and then you take it to 0. That's what the differentiation. If you want, you can expand this and get 1 minus 6t, then plus 9t squared, then you differentiate that. It sounds okay, no problem. But if you know how to differentiate this, the better. Okay, so that's it. Now, if someone wanted to here to get, if you can also get t when you dot this with this and you equate it, so that's what we call the vector approach. But you've seen also that vector approach in our last lesson. So that's it. I wish you well. Yeah, hope you can see the alternative here. Alternative, you can dot this, then dot this, equal to 0, and then you get it the same way. I think you see that the same answer there. So either use this is what we call the vector approach, this is the differential approach. So either use this or this, all of them will be giving you the same value of t. Anyway, see you.